So good evening, buenas noches, everybody. Welcome to day one on week 2 of the semester for Chemistry 112. Last week on Thursday, the last thing that we talked about was the organization of the periodic table. We learned that when it comes to the periodic table, there are groups, and the groups in the periodic table are going to be the columns. In addition, we learned that certain columns have a specific name. In addition, we also learn about the periods in the periodic table, and you can see here how the periods are labeled by my highlighter that is in pink, and the periods in the periodic tables are going to be the rows. We did 2 examples when it comes to this material. We were able to, given information, determine what period or group number that refers to, and in addition, we were able to also determine, if we're giving a group number and a period, determine what is the element and symbol that refers to. Before I continue, any questions on this concept? If you don't have any questions, put a 1 in the chat so we can continue talking about chapter 1 material. Great, love to see those ones. So let's continue talking about the concepts of chapter 1. And now we are going to move on to understand math concepts when it comes to measurements in chemistry. So in section 1.3 in your textbook, we are going to talk about what is a measured number and what is a significant figure. As you can see in the slide, in science, in healthcare, in business, we often have a measurement, or we report a value. The definition of a measurement specifically is going to be a definite magnitude of quantity, capacity, or dimension that is adopted by convention or by law, okay? When it comes to the laboratory, scientists utilize the metric system of measurements. We as scientists have adopted a modification of the metric system, which is known as the International System of Units. For short, we call it the SI system. You guys can see in the following table that we have in the slide a list of selected measurements. As you can see, length, volume, mass, temperature, time. And then in the second and third column, we have different types of measurements that correspond to those. So as you can see, meters is going to be what we utilize in the metric system for length. And you can see that in the SI system, we also utilize meters. Now, in addition, we can see that in parentheses, we have the abbreviation for those measurements. So this is just to give you guys some examples of specifically the different types of measurements that we may encounter in everyday life. Now, the image that we have here to the right of the slide are representing specifically people that most likely, by looking at what is on the table and what they're consuming, they went to brunch. So when it comes to measurements, okay, that we see on the left side of the slide and the image that we see on the right side of the slide, what are some measurements that we can observe in the image for the people that are eating brunch? So let's just put them in the chat, or you can unmute yourself. What kind of measurements can we see? Great, temperature. So what would be the example of temperature in the image?
That they're drinking like a hot beverage, or maybe one's drinking a cold beverage.
Excellent example. I see that some people put mass. What would be an example of mass? Which means, that we're looking at the amount of matter in somewhere. What would be the example? Oh, I see that some people put coffee. Yes, like if somebody has a larger amount of coffee compared to a smaller amount of coffee. Great answer, Elizabeth. The people themselves, depending of, the figure of the person, we can say like, oh, okay, these people have different masses, okay? And as you can see, these measurements is something that we encounter in everyday life. Now, taking that into consideration, one of the things that we're going to learn now is how actually derive measured numbers, okay? So when it comes to measured numbers, understand that these are numbers obtained when you measure a quantity. You maybe know how to measure. If I give you a ruler, you may be able to determine. But now we need to take into account how we actually write these measured numbers in the laboratory. And this is how a measured number goes. A measured number, you need to write it such that you express what is going to be the observed numerical value based on the marked lines that we have. And you're always going to have an estimated value present in it. Now, that estimated value is always going to be the final number in your measured number. And we always have to include the unit of our measurement. To see an example of this, I'm just zooming in into this object. Here we have a drawing of a pencil and I have a ruler in centimeters, okay? If I use a line to just determine what is going to be the measurement of this object, okay? Remembering that when I have a measured number, I'm going to have known digits. And remember that the known digits are going to be what you can see in the markings. What are the known digits here? Let's put it in the chat. What is the known digit for the measurement of this pencil based on this ruler?
1 to 10.
10. Excellent. Now, we also going to have an estimated digit. And I'm going to, again, because I'm just writing it in words, separate them by a comma, but we're not going to put a comma between the digits. So we're going to have our known digit, and then we're going to write our estimated digit. And the reason why estimated digits exist is like, if we look at this object, we can see that it's actually more than 10, but it's less than 11. So whenever we have that estimated digit in this measuring device, the first decimal place is going to be our estimated digit. So how do we know what is our estimated digit? Mentally, we're going to write 10 lines between 10 and 11, okay? So when you look at this, maybe some students are going to be like, you know what, Dr. Luz, I look at this and I think that this is 10.7. There may be another student that says like, well, I think this is 10.8. Okay. Now, which one of the two measurements is more correct? The 10.7 or the 10.8? Which one is more correct? People are saying 10.8. You know what, you guys? Both are correct. And you know why they are correct? Because they're estimated digits. So that last value, because it's an estimated digit, it could be 10.7, 10.8. Maybe some students may be like, this looks like 10.9, okay? That last value, as long as you estimate correctly, right? Because if we estimate 10.1, that doesn't quite look right, because this is more than half past the 10 line. It's close to 11. Now, lastly, when we are writing our measured number, the last thing that we write is the unit of measurement. So in this case, it's going to be centimeters. And both measurements are okay, even if you decide 10.9. Because again, that last digit is always an estimated digit. Always, always, always. Now, that always depends on the ruler that we're using. Whenever we're measuring volume, we also keep in mind that these rules also apply, okay? So let's do a couple of examples so we can, solidify this concept. So here I have this object, okay, which is this drawing of a red rod. So I'm going to write a dotted line here. And I want you guys to see that I have two rulers, okay? The one on the top versus the one on the bottom, okay? Depending on the instrument that we utilize, understand that the numbers that we're going to write for our measure value are going to be different. So the ruler on the top looks the same as the ruler that we just utilized. So if I'm measuring this rod with the top ruler, because my markings only show me the whole number, my estimated digit is the first decimal place. So what would be a measurement that we can write for that object with the top ruler? 9. Excellent. 9.4 centimeters. Because I know that this is at least 9, but it's less than 10. And my estimated digit is going to be that first decimal place. Now, I want you guys to pay attention to what happens in the bottom. If we look closely to what happens in the bottom ruler actually has the markings for the whole number and for that first decimal place. And if we even look closer, okay, we can see that that line that I drew is a little bit past that 9.4. So what happens when we have a ruler that illustrates the whole number and the first decimal place? In that case, then I know that my ruler, the known digits are going to be the whole number and the first decimal place. So what is my estimated digit? That second decimal place. So when we look at this closely, again, I'm just zooming in. Some students may be like, you know what? I think that this is 9.4, but then I'm going to do the estimated digit. So if I'm using the bottom ruler to measure my object, so the correct way to report it will be like 9.41 centimeters. And again, the 0.01 is my estimated digit. You could have said that, oh, I see it right at 9.4. Then you could have said, oh, the measurement is 9.40. Again, the bottom ruler has a marking for that 0.4. My estimated digit is the second value that I see after that 0.4 because it is in the marking. So taking that into consideration, take a minute, okay, and determine, I'm going to just write a line here. This image of a paper clip, determine the measurement for it with the top ruler versus the bottom ruler. So I'm going to give you guys a minute to do that. What is going to be the measurement that we report if we had as a measuring device the top ruler versus the bottom ruler? Great, thank you for putting in the chat, you guys. I agree. 5.8, 5.9 will be what we report for the top. Great job. What about the bottom ruler? What would it be? When we look closer at it. Excellent job. So we can say, well, it's really close to 5.9, or maybe there's somebody that's like, no, I think it is 5.9. But I like, it could be 5.89, 5.90. Those are correct. Because again, in the bottom ruler, we have markings for the whole number in the first decimal place. So the second decimal place is our estimated digit. So let me just write those notes right here. So we can have 5.88 or 5.89 centimeters, or 5.90 if you see it right on the line, centimeters, okay? Now, this whole skill of measuring objects with rulers actually also applies when we're measuring volume. So when we are measuring volume, let's understand that when you put certain substances in glass or in plastic, they may create what is known as a curvature, and the technical term for it is called a meniscus. That is the word that we see to the left of the slide, okay? So the meniscus is this curvature that just comes from the idea of your substance interacting with the container that it has. Now, that curvature, you can see that it is pointing down, and that means that that is a concave meniscus. But understand that there are substances that have that curvature pointing up, and that is a convex meniscus. So how do we deal with having a meniscus for a certain substance? As you can see, if my substance has a curvature pointing down, then pretty much I'm going to take my measuring device, and typically this is for volume. And then what we're going to do is say, well, my curvature is pointing down. I'm going to put my instrument where at the eye level, I can look at the bottom of that curvature. And that's how I determine the volume that I have of this liquid in this container. So when we look at the example that we have on the left, and we look at the markings for this device for measuring volume, we can see that this is 30, and then each line is 1 milliliter, 31, this is 32, 33, 34, 35, so on and so forth, up to 40. So if we need to determine the volume of this liquid that is in this device, utilizing the same concepts that we did for measuring length that we just discussed, what will be the volume that we see in the image on the left? How many milliliters would we have? Excellent job. We know 36 is our known digit, and then from there, we're going to estimate. And I like what I see. Some people are going to estimate 36.5, 36.7 milliliters, okay? So again, it's all relative. When it comes to measurements, there's always that estimated digit. Let's say that when I'm measuring this, I say, okay, this is going to be 36.6 milliliters just because I see it a little bit higher than halfway, okay? Again, 36.5, 36.6, 36.7 are also correct. So to solidify this concept, I have another image of a volume glassware. And you can see here that we have a substance that has a meniscus, okay? Now I want you guys to pay close attention to the markings in this volume device, okay? When we look at the markings here, we see that the large line, that's 6. But as we move up, this is 6.2, this is 6.4, this is 6.6, this is 6.8, this is 7 milliliters. Because you can see that there's 5 markings from that 7 all the way to 8. That's how I know that every single one of those spaces is actually 0.2 milliliters. So taking that into consideration and looking at the curvature of the liquid that I have in my container, what will be the volume that we report for that second image? Let's put it in the chat. Thank you, Isaiah. Thank you, Vanessa. You guys need 2 decimal places. Thank you, Kiyomi. Thank you, Katie. Remember, here my markings are the known digits is the 6.6. So then I write a second decimal place because my markings are the known digits. Those I must write, but I must also write in an estimated digit. And I love what I see here. Thank you, Natasia. So when it comes to this, I can say, well, based on that curvature, I'm going to say that this is 6.61 milliliters, okay? Because I know that my 6.6 is a known digit because there's a marking for it in my instrument. And then the second one is an estimated digit. Any questions when it comes to measuring length or volume or writing measured numbers? Then let's move on to the next concept.
Oh,
Go
sorry.
ahead.
I was just going to say, I have a quick question, if that's okay.
Yeah.
Is the standard of practice always to, when taking a measurement, always to record 1 decimal point of estimated digit?
So it depends on the
Or
instrument.
does that like vary? Like, so when we're asked, you know, to provide a measurement in lab, are we always generally going to use however many decimal points we can of known digits and then 1 decimal place, 1 estimated digit?
So the rule of thumb when it comes to that is that it depends on your measuring device. Your measuring device on the top, it only has whole numbers. So the first decimal place is the estimated digit. So take that from the point of view of like, what is my measuring device showing me? Like the top ruler only shows you a whole number. So the first decimal place is your estimated digit. You must always in a measurement have known digits and an estimated digit. In the bottom ruler, your known digits are whole number and first decimal place. So the second decimal place is your estimated digit. When we have the volume, same thing. The reason why we only have 1 decimal place in the example on the left is because my known digits are only the whole numbers between 30 and 40. So that first decimal place is my estimated digit. In the second example, my markings show me whole number, first decimal place. So that second decimal place must be included always. So it depends on
Okay, I got you. So I think you said in there that you always have an estimated digit. So there'll never be a case where we're only using known digits, or kind of on the other end where we're using like 2 estimated digits. It's always
So-
like all the known that you can plus 1 estimated.
Yes.
Okay.
That's the correct way to think about it. Because for example, in lab, people will look at that second image that I'm showing right now and say like, oh, 6.6 and calling the day. The problem with that is the next topic that we're talking about, which is resolution. Every instrument that we utilize in the laboratory, if we're measuring length or we're measuring volume, has a resolution. And you can see that when it comes to resolution, that is the quality to which an instrument can be read. Some instruments are going to show you a lot of digits. Some instruments are not going to show you that many digits. That's why it's important that when you write a measure number, you need to include the digits that are shown, because that gives you a tie into the resolution of the instrument.
Oh, I see. I got you. Okay. Thank you so much.
No problem. So tagging along with the whole idea of resolution. So I'm illustrating here to you guys 2 different types of instruments that we have in the laboratory for measuring mass, okay? The instrument on the left is known as an analytical balance, okay? And an analytical balance, as you can see in the screen, is going to show you many digits, okay? When we look at the image, the instrument on the right, okay, this is also a balance. But when we look at the screen, you don't have that many digits shown specifically in the screen. What does that mean in terms of resolution? Since resolution by definition is the quality to which an instrument can be read, out of these two instruments, the analytical balance will have a better resolution. Compared to a top loading balance, because in the screen, you don't see that many digits. Understand that in the laboratory, the more digits that you can see, in other words, the better resolution an instrument has, that means that it's going to cost more. So while a top loading balance for laboratory purposes could be in the mid, like $50, $75, $100, an analytical balance can be a couple hundred. On the lower end, they could be $500, or they could be a couple $1,000, just from the fact that they have a better resolution and they show you more digits. Understand that all of this has to do with experimentation. It depends on what you're trying to do in the laboratory that you may need to utilize the analytical balance because you want a better resolution. And sometimes you don't need that much of a great resolution, so you will be using the top loading balance. So it depends for the use and the experiment that you guys will be performing. Now, why is it important that we know this? Because as you can see, the second term that we have here is significant figures. Significant figures by definitions are going to be, when we have a measured number, these are going to be the digits that carry meaning, contributing to a measurement's resolution. So those digits that we see on the screen, since they are tied to the resolution of the instrument, that actually is what a significant figure is. It's not, so we have to basically extract ourselves from common language when it comes to significant figures. Because I find that whenever I'm teaching that concept, people are like, oh, that means that that digit is not important. It's not that it's not important. It's just that understand that there's certain digits that are going to contribute to that measurement resolutions, and other digits are there to tell you quantity, if you have a large measurement or you have a small measurement. So taking that into consideration, let's now review the rules for determining significant figures and learn how to determine the significant figures in a particular measurement. So these rules are just a summary for the rules for significant figures, okay? We're going to go through rules 1A through 1D, and then we're going to talk about 2A through 2B. In rule 1A through 1D, these are the terms. So when do I know that a particular measurement, and you can see in the second column, different examples of measurements, am I dealing with a significant figure? First of all, a number is a significant figure if it's not a 0 digit. So as you can see, 4.5 is going to have 2 sig figs. 122.35, because all of the digits are not 0, all of them count as digits that carry meaning to the resolution. Now let's deal with the zeros. If your 0 is in between non-zero digits, then all of the digits are significant. So you can see 205, 3 sig figs. 5.008, 4 sig figs. Again, your zeros are in between non-zero digits. Rule 1C states that a 0 at the end of a decimal place is significant, okay? But when it comes to rule 1C, understand that it needs to meet two parameters. Those parameters are that you need to have a written decimal place, and you need to have the zeros after non-zero digits. So your measurement needs to meet those two statements in order for all the digits to count. So if you look at the first one, 50 decimal place, that has two sig figs. 25.0, that has three sig figs. Again, the zero is after the non-zero digits, and there is a written decimal place. Go ahead, Rachel.
Oh, thank you so much. I was wondering about the last example, the 16.00. Wouldn't there just be three significant figures there? Because the second zero, the one before it is not a non-zero digit.
No,
Like
because
it's a zero
we are
after
not-
another zero, right?
No, but then this is the thing. Let me rephrase that for you. Are both zeros after non-zero digits? So we're not looking specifically what is right before it. It's like if they are after non-zero digits.
Oh,
Right?
okay.
Both zeros
yep,
are
yep.
after non-zero digits, right?
Yep.
So that's
I
why
gotcha.
they're both significant.
Thank you.
No problem. Now, scientific notation is the next topic that we're going to talk about. So understand that if you are given a measurement in scientific notation, basically for scientific notation, anything that it is in the first part before the times 10, they are significant. Let's now deal when zeros are not significant. Again, it's not that the zeros are not important. It's just that they have a specific job in the value for the measurement. And this specific job is to be called a placeholder. So let's look at rule 2A. In rule 2A, it says, when we have a zero at the beginning of a decimal number, it is not significant. Now, for those of you that all of a sudden is like, but wait, you just said in rule 1C that a zero at the end of the decimal place is significant. Let's look at the examples. 0.0004, okay? Remember the two parameters in order for those zeros to be significant. When we look at these measurements, is the first parameter met? Written decimal place? Yes or no? Let's put it in the chat. Great. So at least people are following. Now, is the second parameter met? Are the zeros in this measurement after a non-zero digit? Great. I see the no's. Thank you for the no's. So you know what, you guys? These zeros before the first non-zero digit, they're just telling you that you have a small number because it's less than 1. So their rule is a placeholder, just to let you know that this is a small value. So be careful to not confuse rule 1C with 2A. Let's look at 2B. Zeros, when you have a large number, okay, and you don't have a decimal place written, like 850,000. They're there just to tell you that you have a large value. It's not that they're not important. Their role in this value is just telling you that you have a large number. So we call those zeros placeholders. Rule 2A is also calling those zeros placeholders, because in the case of 2A, you use it for small numbers. Rule 2B, you have it for large numbers. So taking that into consideration, let's practice. Let's determine how many significant figures we have in the following digits, okay? Let's go through the first one. Let's put it in the chat. 700,000. Great job. This has one sig fig. My shorthand for sig fig is SF. Let's look at the second measured value. How many sig figs? Excellent job. 6 sig figs. For the student that wrote 5, understand that 0 after the 5 is significant because it's in between 0 numbers. The last 0 is significant because it's after a series of non-zero digits. Number 3, how many sig figs in that measurement? Thank you, Brayden. Thank you, guys. This has 5 sig figs. What about number 4? Number 4, how many sig figs? Excellent job. Thank you, Vanessa. This has 6 figs. All of those zeros are significant. What about 630? How many sig figs? Excellent job. 2 sig figs. Lastly, 20 decimal place. Great job. This has 2 sig figs. Okay. Questions about sig figs? Then let's move on to the next concept, which is scientific notation. So sometimes we're going to have measurements that are really large. Sometimes we're going to have measurements that are really small. When we have that, understand that we need to find a way to write them so we know they have, we have a really large number or a very small number. And that's where scientific notation comes in. It's a method to express very large or very small measurements that we have in the laboratory. Now, we can also use scientific method in calculations. So to give you guys the example of a very large number, you can see that the diameter of planet Earth is a very large number. That's like 12,756,000 meters. The mass of one virus. So if you have, you know, many viruses, this is just one virus. As you can see, this is 0.00000. And there's like 14 zeros here, grams. So we have to find a way to write these values, okay, in scientific notation. So this is how we write scientific notation. When we write in scientific notation, then understand that for large values, we are going to move the decimal place that may be written or implied from right to left, such that we create a value which is called a coefficient that is at least 1 but less than 10. So if we have 2,400, there's no decimal place that is written, but there's one that is implied. So when it comes to that, the decimal place is right here. You see this label for 3 places. That's because we took that decimal place and we went 1, 2, 3 times. Now I'm going to write that as 2.4. And since I moved 3 places from right to left, this represents the exponent in my power 10. What if I have a small number? Okay. If I have a small number, I'm going to move the decimal place from left to right. Again, so I get a value that is at least 1 and less than 10. 1, 2, 3, 4 times from left to right. So now that's going to represent my coefficient. That's where we get the 8.6. We write this as times 10, but since we move from left to right, this number of places represent what we have as an exponent. And since we move from left to right, now our exponent is negative. In the top, since we move from right to left, our exponent on the times 10 is positive. Let's actually do some problems when it comes to changing things into scientific notation. We're going to do the first three. So take a moment as I go through it. How many places am I going to move that decimal place from left to right to create a coefficient of at least 1 but less than 10? Excellent, I like to see that. We're going to move this 1, 2, 3, 4, 5, 6 times. Now our coefficient is going to be 1.85 times 10. And since we moved 6 places from left to right, then this is going to be -6. Okay, let's look at the next one. How many times do we need to move that decimal place in order to get a value between 1 and less than 10? Only 1 time. Great. Now, all these measurements that I'm giving you guys are in regular notation, and we need to change them to scientific notation. Let me explain something about some of the values that I see here, because we just learned this. How many sig figs here? Thank you, Atasia. 3 sig figs. So guess what? When I change this value into scientific notation, I need to keep the number of sig figs. You may be like, but why do I need to do that? Isn't 6.00 the same thing as 6.0? No. Because remember that if you drop the number of sig figs, you're affecting the resolution of your instrument. So the coefficient for this is going to be 6.00. I cannot change the number of sig figs going from regular notation to scientific notation, because again, I'm affecting the resolution of my instrument. So when it comes to this, I'm going to do times 10. I have to move this only once from right to left. So the value here for my exponent is going to be 1. Let me include the unit. Let's look at letter C. In letter C, again, I have to move the decimal place so I get a value that is at least 1 but less than 10. Do I have to move that decimal place? Do I have to move it? Yes or no? Great. I'd love to see that in the chat. No, I don't have to move it. So how do I deal with a measurement like that? I still have to express it in scientific notation, but technically I don't have to move the decimal place. You can still express it in scientific notation. All you have to do, you guys, is say 6.7 times 10 to the 0. Why times 10 to the 0? Thank you so much, Elizabeth. Because 10 to the 0 equals 1. Okay, so this is how we change our values from regular notation to scientific notation. Any questions? Put a 1 in the chat if you're ready for the next topic. Put a 2 in the chat if you know how to round. I will just do a few examples because I know that sometimes this is a topic that students are like, what? I don't know how to round. The rules for rounding you see on the left side of the slide. But just to review really quick, a number of you know how to round. when we have a measurement, if you have to round, understand that if the digit next to what you're interested in is 5 or more, you add 1, and then the rest of the digits are dropped or they're turned into 0. If the digit is less than 5, then nothing changes to the digit that you're interested in. Let's look at the examples that we have here. Let's say that we have the measurement 10.253. Okay, we have to round it to 3 sig figs. But when I look at this measurement, you're going to say, okay, these 3 are my significant figures. Okay, so now because the 2 is next to 5, that means that that 2 is going to change to a 3. And in this instance, the rest of the digits are dropped. So when I round this measurement to 3 sig figs, the final answer is 10.3 meters. Okay. Great job in the chat. What about the second example? I need to take 25.01 kilograms and I need to round it to 1 sig fig. So when I look at this, the 2 is what I'm interested in. The 2 is next to the 5. Okay. Thank you for the students that put 30 kilograms. And this is why 30 is the correct answer. So the 2 changes to a 3. I agree with that. But now in this case, the 5 turns to a 0 because the 2 is in a 10th place. So think about it. It's kind of like in a number line, right? If this is 20 and this is 30, 25 is right here. So it cannot be just 3 because 25 is going to be closer to 30 because that 2 is in a 10th position. Let me just do one more to make sure that you guys know how to do this. Let's look at the third one. 204.7 milliseconds, rounded to 3 sig figs. Excellent job in the chat. 205 milliseconds. Questions about rounding? Okay, put a 2 in the chat if you're ready for the next topic. So we have talked about measurements. We have talked about what they mean. We have talked about sig figs, what they mean. Now we are going to deal with how do I know that if I am taking measurements and I'm adding or subtracting or multiplying or dividing, how do I know how many sig figs I'm supposed to report? Okay. On the left side are the rules for addition and subtraction. On the right side, multiplication and division. So when it comes to addition and subtraction, okay, when it comes to sig figs, if you're adding or subtracting, you can see that the final answer is written, so it has the same number of decimal places. I cannot stress that enough. Decimal places as the measurement with the fewest decimal places. So you can see here that we have 3 different measurements. The first one has 3 decimal places, 2 decimal places, 1 decimal place. The first value that we see here, this is our calculator display. Calculators don't know sig figs, okay? You need to remind yourself that, okay, I need to express my answer with the correct number of sig figs. So you're going to take your calculator display and you're going to round it to the correct number of decimal places, which here, the smallest number of decimal places is 1 decimal place. For those of you that will or have already checked chapter 1 chapter quiz, having no decimal places is the smallest number of decimal places. So if you don't have any decimal places, make sure that your final answer basically is rounded to no decimal places. Keep that in mind, okay? Let's go to multiplication and division. When I have multiplication and division, okay, my final answer is written so it has the same number of sig figs as the fewest sig figs. You can see here, we're multiplying two values, 24.66 times 0.35. Our calculator display is 8.631. The first measurement has 4 sig figs. The second measurement has 2 sig figs. So even though I have this calculator display, I need to round to 2 sig figs because again, I am multiplying. So here we have examples of doing multiplication, division, addition, and subtraction. So at this time, at least, I want you guys to practice. Let's do number 1 and let's do number 3, okay? So take a moment. You can put it in the chat if you are ready with a calculator. What is the answer for the first one? Thank you, Katie. 25.6 plus 36.27 gives you a calculator display that is 61.87. Just like it was shown. Thank you guys for all the other students that also put it in the chat. Since the smallest number of decimal places here is 1 decimal place, that's why we need to round to that. So that's why we will say 61.9. Let's do number 3. Take a moment, put it in the calculator, put it in the chat. 6.2 times 4.114. 6.2 times 4.114. Excellent job. Okay. So for number 3, we're multiplying. So we have to look at sig figs. Let me write these notes because I know that some students are visual learners. Let me just zoom in. 1 decimal place, 2 decimal places. This is based on 1 decimal place from the value 61.89. So in here, when we multiply these two, okay? 2 sig figs, 4 sig figs. So even though my calculator display is 25.5068, how many sig figs do I need to round? Great job on the chat. 26. Okay? Because I need to express this as 2 sig figs. Okay?
And this is 2 sig figs because we're for multiplication, it's the lowest significant number.
Exactly.
Okay.
Also for division. So if you were doing number 4, how many sig figs do we need to round to? Let's put it in the chat. So for number 4, so multiplication and division is the same rule. How many sig figs do we have to round to on number 4? Not 2. Excellent job. 4. Because 7.331 has 4 sig figs. 12.41 has 4 sig figs, so you need to round that to 4 sig figs. For number 2, it's decimal places, right? So how many decimal places for number 2? Because we're subtracting. How many decimal places? Great. Now, I only have about 12 minutes of lecture left. What I'm going to do on Thursday is that I'm going to explain to you guys how to do 5 and 6. The reason why I'm going to take my time and explain it on Thursday is because when it comes to a little bit of more meat in our equations, meaning that we have to apply PEMDAS rules, okay? It's going to be a little bit of a longer discussion, and I want to at least go over conversion factors with you guys today, okay? But are you guys good with the rules of just addition or subtraction or just multiplication or division? Are we good with that? Go ahead, Rose.
Okay, so for number 6, you know how there's multiplication and addition? How would you know how many significant figures to do for that? Would it?
Like I just said, I'm going to go over it on Thursday.
Okay.
Because if I go over 5 and 6 right now, I will not talk about conversions. And for you guys to do your pre-lab, I need to go over conversions. So
Okay,
I'd rather
thank you.
go back to 5 and 6 on Thursday and just talk about conversions today. No problem. What I will do, let me just write it in my calendar. I'm going to post videos on YouTube for sig figs.
Where can we find the link? I was having trouble with that. Do you post a link in the Zoom chat after the lecture's done?
For the lectures themselves,
Yes.
if you go to Canvas, on Canvas, you guys are able to find all of this. Let me show you here. Let me log into my Canvas. So when I go here, student view. So this is how you guys Canvas should look like, okay? And when you go here, you can see that I have a tab for lecture notes. So those are from the PowerPoints. Look at this, lecture videos. I click there, boom, lecture video. And that links you directly to my YouTube channel. So today's lecture, you will see it that I will upload it after I'm done with lecture today. Everything is on Canvas.
Oh, sorry, I was talking about like where you're gonna talk about the sig figs specifically.
Oh, that's just going to be one more module that I add to this.
Okay, that's the one I was talking about. Sorry.
So it's not there. I have to build it. It's a module that I'm going to be adding. So you guys will have videos from, again, people that on YouTube are going to, tutor you in a way, or tutors that I know that are solid when it comes to explaining these topics. So I will just post their links on a tab for you guys.
Okay, last question. Where's the answer keys for the worksheets?
Unless I finish the chapter, I don't post them. Because
Okay.
this is the issue that can occur sometimes. Students look at the answer key, they just download it and they never try a single problem on the exam. So in order to not have that happen, then understand that I only post the answer key after we have finished the concept.
Oh, okay, I see. Okay.
So you can try it, but for example, my goal, which right now I only have 7 minutes to go over conversions, is to make sure that we finish chapter 1, because if not, that's going to put us behind, and I don't want to be behind the schedule on material. So if anybody has other questions, please stay after class. I'm more than happy to answer those questions for you guys. But right now, I only have a couple of minutes left, and I would like to at least give you guys resources on how to do conversions. I will also post videos from tutors about conversions, because I know it is a topic that is important in chemistry, and sometimes it can be complex. So taking that into consideration, let's move on to section 1.3, which is talking about unit prefixes and conversion factors. So one of the main features when it comes to the SI and the metric system is going to be specifically a term that we can add in front of any unit to increase it or decrease it. So in this table, we have common prefixes in the top 4, tera, giga, mega, and kilo, make any unit large. Deci, centi, milli, micro, nano, pico are going to be prefixes in front of any unit that will make them small. So if you guys see, for example, milligram or micrograms are going to be smaller units compared to a gram, which is just the basic unit where we start, okay? Now, why is this important? Well, these prefixes, as you can see, are related to one another by factors of 10. Even though the list for prefixes is more extensive than this, I want you guys to at least know these: tera, giga, mega, kilo, deci, centi, milli, micro, nano, pico. Those are the ones that I want you guys to know, okay? So make sure that you know these for exam 1. Now, understand that when it comes to these metric prefixes that exist, we can use them in relationship in what is called equalities. And equalities by definitions are going to be 2 different units that describe the same measured amount. And for the prefixes that I just introduced to you guys can see that we have the relationship between kilometers to meters, or the relationship between meters to millimeters, the relationship between centimeters to millimeters, so on and so forth. So this column that you guys see here, the metric system, okay? I'm going to show you guys a technique that is called the number line method to do those conversions. We also have US units and metric to US units, and you can see the relationships here. Understand that when it comes to exams, my expectation, you guys, is that you have all of your notes taking the exam. So I'm going to mention it also once we get close to exam 1. You can take and use your notes for exams. That's my expectation, because I'm not going to be policing you and seeing like, did the student use the notes or not? Hey, let's be clear. Use your notes. Is only to your advantage, okay? So basically the exams in this class is going to be open notes, okay? I hope that at least give people a little bit of a breathing room of like, oh my God, I can use my notes. That's great. But going back to this, here we have in the second column and on the third column, US units and metric US. Now, let's understand that whenever we have a relationship between 2 units, that is known as an exact number, okay? So It's 7:18. I'm going to extend my discussion a few more minutes, okay? So just in case. So whenever we have, again, these common equalities, they're known as exact numbers. Why is it important to establish that? Because if we have equalities, again, the numbers that we see in the equalities, we're not going to count them for sig figs. So whenever you guys are doing conversion factors, which is one of the questions in the pre-lab, understand that based on the sig figs given, that's how you know how many sig figs you're going to have in the final answer. Remember that rounding is implied. So right now, let's just do 2 examples for how do I do conversion factors, okay? When it's metric to metric, and when I have some things that are part of the equalities that I also see in this table, okay? So let's just deal with that, because I want to at least give you guys this. So the following example reads, a doctor makes an incision that is 2.5 centimeters long. And we're just trying to find what is the incision in meters. So I just mentioned to you guys that I have a method that is going to be the number line method. In the number line method, all I did, you guys, is just take the prefixes and make them in a line. Since the relationship between each other is by tens, all you have to do when you have metric to metric conversions is move the decimal place. So in the example that we have here, we have 2.5 centimeters. And we need to change it to meters, okay? Great job in the chat. When we look at this, we say, okay, I see T, I see G, I see M, I see K. Those are the abbreviations for the prefixes. So that M is not meters, that M is for milli. Where do I find meters here? As a basic unit. So, see how we start at centimeters? So we start here, centi. I am walking to meters. I need to move that decimal place 1 time, 2 times from right to left. So look, just like it was shown in the chat, I need to move this 1 time, 2 times. Oh, I open a pocket right there. How do I fill it? I fill it up with a 0. So that's where the answer 0.025 or 0.025 comes from. Again, what is given, I mark, and then I move to see how many places I have to move the decimal place to the right or to the left to change between the unit given and the unit wanted. So that's for metric to metric conversions. Let's look at the bottom one, okay? What is the weight in pounds of 11.63 kilograms of masa for tamales? Sorry if I'm making anybody hungry, okay? So the relationship between pounds and kilograms is in that table that I showed you guys here. It's right here. Now, you can see that 1 kilogram equals 2.20 pounds. So how do I do that? Well, I know that my equality is 1 kilogram equals 2.20 pounds. So I write the unit given, 11.63 kilograms. My equalities can be turned into a fraction. This is called dimensional analysis. How do I know how I'm going to write this as a fraction? We always want to cancel units diagonally. So if I want to cancel kilograms, I need to put kilograms here. I put the value next to kilograms, 1. On top of that, I put pounds, which is what 1 kilogram equals to, 2.20 pounds. So how do I enter this into my calculator? 11.63 times 2.20 divided by 1. That's how I enter it. Now, when I do 11.63 times 2.20, I find a calculator display of 25.586. This has 4 sig figs. I need to round my answer to 4 sig figs. Kilograms cancel with kilograms. So I see a lot of people rounding. I need 4 sig figs. So my calculator display tells me 25.586. Excellent. 25.59 pounds is my final answer.
I thought when multiplying and dividing, it's the least amount of sig figs.
But like I said, this is an exact number because it's part of a definition. When we are using those in sig figs, because that is an exact number because it's part of a definition, we are not counting it in the sig figs. You're basing your sig figs on the measurement given. So these equalities that we have do not count for the sig figs. Put a 1 in the chat if making the pre-lab due on Friday will help you. Because I know that there's a number of you that maybe need more practice. You need to let this marinate. I'm okay with changing it to Friday because that's not going to affect me. I just want to make sure that you guys get these concepts for the lab. Okay, so I will do that after class. I'll change the deadline. I will also put the resources. No problem. For the students that are like, but I already did it. You have a second attempt. Use it to your advantage. So in the pre-lab, I put a second attempt. So if you want to go ahead and redo it, please do so. If you're okay with your grade, then don't do it. Okay? So this is all for today. Let me just stop the recording.